this is kicked off by Mazharul Islam, who's going to talk us about passkeys again, but this time detecting compromise of passkey storage on the cloud.
So, hi everyone. My name is Mazharul Islam, and I work on developing machine learning and cryptographic techniques to safeguard online users from emerging threats. This is a work that I did when I was in my final year of my PhD with my colleagues from University of Wisconsin-Madison and Visa Research. So, as the last speaker nicely summed up, that we are transitioning from passwords to passkey for online user authentication. And a few years back, Apple announced that they are rolling out support for passkey. Google, Microsoft followed their path very soon. And as a result, if you register your account online, when you are registering your online accounts, you may have been prompted by this kind of screens to create passkeys. I will just go over how the passkeys work at a very high level so that we can contextualize what is the exact security threat that we address in our paper. Under the hood, passkey-based user authentication is an asymmetric signature scheme that is prescribed by the FIDO 2 Alliance. During the registration, user's device creates two keys. One is the private key SK, and another is the public verification key VK. The SK, which is commonly referred to as the passkeys, stays on the user device, and the verification key gets sent to the relying party, and the relying party saves it on their credential storage. During the authentication phase, the relying party sends a random challenge to the user device, and the user device can successfully complete that, sign that challenge using the private key or the passkey they have created during the registration phase. And the relying party, once the signature gets sent to the relying party can verify the signature and allow the user to log in. It gives an extra layer, extra security assurance to the relying party because passkeys, as we were talking earlier, passkey was never supposed to leave the user device, it's user device bound, and it's not guessable or it's not phishable. However, under the hood, there was a big usability concern that was looming. That what if users lose their access to their device, and then in that case they won't have access to their passkeys, and they would be locked out from their account. And this account lockout problem has been one of the main usability issues that was hampering the wide adoption of passkeys. So welcome to the world of synced passkey. This is an industry-adopted solution to solve the account lockout problem. This is very simple. Whenever the user creates a passkey, it is backed up on a cloud storage by a passkey provider. And if the user loses their device, they can just readily download the passkey from the passkey provider's cloud storage. And iCloud Keychain, Google Password Manager, Google Password Manager, Password Monitor from Microsoft basically does act as passkey provider for their own customer base. Unfortunately, this creates a new security threat. What if the passkey provider is compromised and attacker has unauthorized access to users' passkey storage? In that case, the attacker can take the leaked passkey and readily log into user's account at different relying party. And the threat of this type of credential leakage is not new. This has been happening for passwords as well, but for passkey, it's even more worse because many relying party may not even trigger two-factor authentication or any kind of alarm if the logging request is coming through passkey, because passkeys are deemed more secure than passwords. So in this research, we asked that how can we enable the relying party or the websites to detect unauthorized login that are coming as a result of attacker compromising the passkey provider and using the leaked passkey to compromise victim's account. So to find answer, we designed the first framework that is compatible with existing passkey implementation called CASPER, and it can detect if whenever attacker is using leaked passkey to log on to user's account. CASPER, as I will mention in the next few slides, is a decoy or deception-based detection mechanism. And this is not similar as existing literature on decoy passwords, because in decoy password, the relying party has the credential storage, and the credential leakage happens on the relying party's side. However, here for CASPER, we want to allow the relying party to detect compromise of the passkey storage from the passkey provider. So the credential leakage is happening on another party, and the party who wants to, and another party wants to detect that leakage. It turns out identifying the effectiveness of CASPER is also not straightforward. So we use model checking experiments to identify what should be the system parameters and what should be the detection rate, true detection rate of CASPER. Lastly, we also provide a prototype implementation of our existing passkey provider and confirm that it does not have like performance overhead and poses minimum deployment burden. So let's start with a strawman solution to see why this problem is very interesting. So let's say that we to protect users' passkey, before uploading the passkey on the cloud storage, we will encrypt that. And once the attacker gets access to the passkey, once the attacker gets access to the cloud storage, they will only see encrypted passkey. The encryption key could be derived from a user high entropy password that is remembered by the user, something like a master password, or from a key that is created by or a cryptographic key that is created by one of the devices of the user they have access to. However, this idea does not work. This solution works, but except it does not. Because think about it, while securing users' passkey, we also want to make sure that we are not reintroducing the account recovery problem. And this strawman solution, unfortunately, it does that. Users tend to forget their high entropy passwords. We can't blame the user for that, or we as users lose devices from time to time, and as a result, we would be locked out from our account. So the idea that came to our mind is that can we leverage low entropy secret and use that low entropy secret for detection? So at a first glance, this idea should not work, because in traditional defense, any guess on the low entropy secret that is successful by the attacker will render the whole security defenseless. Here, attacker has the advantage. But if we can play a deception game with the attacker by planting decoys, then if attacker steps one of the decoy while performing the guess, then we will trigger an alert, and the relying party would be able to detect that the request is actually coming from with a high probability that the request is coming from an attacker who has compromised users' passkey from the credential storage. So the idea is here that our framework CASPER carefully plans decoy passkey or decoy verification key, and it can detect whenever attacker is using leaked passkey from the passkey cloud storage to compromise user's account. So CASPER achieves this in 3 steps, and the first step is happens when the user creates an account with the passkey provider. So you can think of it as like whenever you are creating your Google, Microsoft, or Apple account. We will generate under the hood a set of detection secrets, decoy detection secrets. And the next step happens whenever the user is creating an account on a relying party. Using those decoy and real detection secret, we will generate decoy verification key. And the third step happens whenever the relying party receives a logging request. If the logging request corresponds to a decoy verification secret, then the relying party would alert detection compromise. Otherwise, they would allow the user to log in. So this is in one slide that you need to know about CASPER in one glance. In the next few slides, I will go into a bit more technical detail. So as I mentioned earlier, in the first step, the provider account setup, the user, under the hood, whenever the user creates an account with the passkey provider, we randomly generate a set of K plus 1 detection secret. One of the detection secret is a real detection secret. The other K are decoy detection secret. These detection secrets are uploaded to the passkey provider, and we are okay exposing this set of detection secrets to the attacker. Additionally, what we are not okay exposing to the attacker is the low entropy secret called ETA. Because this low entropy secret is the secret sauce that we can use to identify the real detection secret. So this is the procedure: select real secret. It takes the set of K plus 1 detection secrets and also the low entropy secret, and we'll be able to identify which is the real detection secret, WI stars. With this process, registration, if the user is adding a new device with the same passkey provider, becomes very simple. The user would download the set of K plus 1 detection secrets from the passkey provider, and we have to take the input the user secret ETA, and the device would be able to identify the real detection secret WI star. So what happens during the account registration? We use the real detection secret WI star and generate an encryption key with the help of a key derivation function, and use that encryption key to encrypt the passkey in a one-time pad manner. So that's called SK tilde. And we will upload the SK tilde, the encrypted passkey, to the passkey provider cloud storage. Note here, the plain passkey, the SK, does not get uploaded to the passkey provider. And additionally, we also have to generate K plus 1 verification keys. And the way it works is that we can decrypt the encrypted passkey using the set of K plus 1 detection secrets that we already have, and we would get K plus 1 decrypted passkey, one being the real passkey and the other being the decoy passkey. And as a result, we also get K plus 1 verification keys. And then we can upload the K plus 1 verification key to the relying, send the K plus 1 verification key to the relying party. There are some more details about that, there are some more underlining tricks that we also have to apply for this protocol to work, but there are some, but you can refer to the paper for that. But this is the main thing that you need to remember about CASPER. And the correctness of the protocol comes that for the user from which we can extract the real detection secret, the I star, then we can get the real passkey, and during the logging phase, we can use the real passkey to complete the challenge from the relying party. So compromise detection is very simple. If the logging request corresponds to a decoy verification key, the relying party would raise an alert. If it corresponds to the real passkey, then it would allow the user to log in. So let's walk through a very toy example how this works. Let's say the user device downloads the SK tilde from the passkey provider. SK tilde is the encrypted passkey, and the user we get from the user, let's say for the sake of this toy example, the user secret is 1234. The user will use the user device will use the correct user secret to derive an encryption key, decryption key, and we will use the decryption key to get the real passkey SK1234. And the logging, and whenever the relying party would see that the logging request corresponds to a verification key 1234, then they would allow the user to log in. Now we can trap the attacker by planting. Let's say for this example, we try to trap the attacker by planting 3 decoy verification key. So for example, we have, in addition to the user secret 1234, we have other decoy user secret 1234, 1235, 1236, and 1237. From attacker's perspective, once they download the SK tilde from the passkey provider, they have to perform guesses on the user secret. And if by mistake, with high probability, they are going to step onto one of these decoy secret. And if they do, then the relying party would be able to see that logging request corresponds to a decoy verification key, and the relying party would be able to tell that it's the logging request, that it's a leaked passkey that the attacker is using to compromise user's account. So there are a few more challenges that we have to solve while designing this idea for CASPER. We have to ensure that decryption using a decoy secret key will always output a well-formed decoy passkey. Otherwise, the attacker don't need to even contact the relying party, because they would be able to readily see that this is a decoy detection secret. So CASPER ensures with high probability for the signature scheme that are supported by FIDO2 that a decryption using a decoy secret will always output a real well-formed passkey. And evaluating the effectiveness of this kind of probabilistic deception-based detection mechanism is not also straightforward. So we run model checking, and for that, by modeling the attacker using Markov decision process and running model checking tools. So here are some results of that of our experiments. That let's say for the example that we planned 32 decoy detection secrets, and the user secret contains only 5 bits of entropy. In that case, the detection accuracy for the most optimal attacker will be detection accuracy for the most optimal attacker would be more than 95%. So initial questions come: how can we instantiate the user secret? Well, there are a couple of ways. For example, we can run a thought experiment that if the user secret is a 1-digit random case insensitive alphanumeric character that is system generated, then it already contains 5.170 bits of entropy. If it's a 2-digit random pin between 0 to 9, it already contains 6.644 bits. So we don't need to have it's very easy to instantiate this kind of user secret in real world to enjoy high detection accuracy. It can also be done using biometric or any type of secret that the user has consistently access to. And with our design, it is almost impossible for an attacker to trigger a false alert. For example, a relying party may want to say that alert the user that their passkeys has been compromised, but in reality, it's not. So in the way we design CASPER is that it's not possible, almost practically impossible for the attacker to trigger such alerts. And one of the main crucial benefit of CASPER is that it offers an extra layer of security to users' account while being deployable, because it is compatible with the existing passkey implementation. It does not have much performance over it. and storage overhead for the relying party. It is also user friendly to the user because all the, apart from the first step where the user where we need to identify the real detection secret, everything is invisible to the user. They don't need to change their daily logging behavior, and the user secret that we use to do the detection only have to have low entropy. So that's in summary, like CASPER traps a passkey breach attacker using decoy detection secrets. It effectively balances all the trade-offs among security, usability, and deployability. And we also run model checking experiments to demonstrate the high detection rate of CASPER. Thank you. Any questions? Yeah.
Is there a general, like the number of decoys used and the bits of entropy, is there a relationship in which it's ideal to?
Yeah. So in our paper, there are 3 parameters actually. I haven't talked about the other parameters. So those 3 parameters we fix one and we experiment with the other 2 and see how the detection rate changes. So for example, if you fix the other 2 parameters and experiment with the number of decoys, we saw that after 32 decoys, the detection accuracy does not increase that much. It saturates.
For any entropy bit, like
for when the user secret has like 5 bits of entropy, 4 bits. This is the general characteristic, the trend we saw. And for the user secret, we fix it. We didn't basically experiment with like 4, 5, 6. But I don't know if there is a linear or like relationship at all. Like after 5, 6 bits of entropy for the user secret, you don't get much gain in the detection accuracy for the same number of decoys. Yeah.
Did you take into account that user can also use a decoy key if they forget?
Yeah. User?
Is it a possibility that the decoy key could be used by the actual user on like an accident?
Yeah, but yeah, so it can happen that so there are a couple of ways to instantiate the user secret. One could be biometric. One could be some secret that the user already has access to. It doesn't have to be always something that the user remembers, but it may happen that the user accidentally steps onto one of the decoy. In that case, we can just reset the passkey or basically, reset the passkey because that alert that goes to the user. So they can readily identify that it's actually a false alert for me because I have mistyped or haven't inputted my user secret correctly.
Actually, my question is a little related to the last part of his question. Is the idea that every single time that you authenticate my device, I have to put the low entropy pin, or is it something that will only happen the first time that I add a new device?
So it will only happen when either you are adding a new device or creating an account for the first time with the passkey provider.
And the usability aspect here is if I only set that pin when I have a new device or when I'm setting up the account, most likely I'm going to, one of 2 things. I'm either going to reuse the same pin everywhere, so it's going to be guessable, or I'm going to forget about the pin if it's random.
Yeah, so this is a future work on like that needs to be explored extensively, like for how users actually manage their secret that is protected by PIN or biometric. That needs more attention. That's for the future work.
Yes, I have a question related to what happens when you detect the use of a decoy. Is there a way to prove some misbehavior or to blame when the decoy is used? Is there a way to blame the service provider and provide a proof that they actually use the decoy as opposed to leak the decoy? Or how can you convince someone that the provider had leaked your decoys?
So you are asking, like, is it possible for the attacker to convince the user that their passkeys has been leaked, whether in reality it hasn't?
Not quite. I'm asking if it's possible for a user to convince another user that there was a leak of its secret, that the service provider was corrupt or attacked.
So, like, convince one user attempting to convince another user?
Or convince the provider, the passkey provider. Like, can you provide evidence from the decoy use that to the passkey provider to evidence that there was a breach?
That's outside the scope of this paper, but in practice, I think it's possible to do. But there might be additional challenges while doing that, but it's outside the scope of this paper. Yeah.
And you're trying to protect the low entropy secret, like the RP shouldn't be able to learn the low entropy secret?
Sorry, can you?
The relying party should not be able to learn the low entropy secret?
Yeah, yeah.
Can you say more about how that's achieved?
So the low entropy secret is not shared with anyone, either with the passkey provider or with the relying party. So relying party does not have knowledge about that. Now, one thing the relying party could do is they look at the verification keys and try to identify they already have the knowledge, which is the real decoy verification key versus which is the K decoy verification key. Now, we have another trick that if the relying party attempts to do so, they won't be able to do that. Like, I haven't talked about that. For example, instead of whenever the logging request corresponds to a decoy verification key, the relying party would raise an alert. Instead of that, we mark a certain percentage of decoy verification key as active verifiers. And only if the logging request corresponds to one of the active verifier, then the alert raises. So that's one of the technique that we use so that the relying party cannot derive the user's secret.
So you have to hide via more decoys.
Okay,
gotcha.
Yeah, but that can happen. For example, user might have 10 accounts on 10 different relying party, and one of the relying party gets compromised. Then they would have access to the K decoy verification key plus one real verification key.
Yeah, good. Thank you.
So I have experiment, actually. I have a slide here as well, but it's very dense. So like there are parts of it. For example, here, if I had got the time, where is that? So here, N is the number of compromised relying party. So when the no relying party is compromised, then you can see that as we increase the number of decoys, as we increase the percentage of decoy verification key, then the detection accuracy increases. But when n is equal to 1, like at least at one of the relying parties compromised, then you can see there is a sharp decrease from here to here. So it's not always a good idea to mark all of the decoy verification key as active if you are considering that one of the relying party of the user, where the user has account, gets compromised. Like n is equal to, here n is basically representing that.
Because they're using, it's different passkeys, but it's the same verification secret, the low entropy secret. Yeah.
Yeah. Any other question?
Well, let's thank Masaru again.